Alright, we're going to try this again because I didn't have the sound on turned the first time. Okay, so the question is, why are S and W the same in the sample program provided? And the answer is pointer aliasing. So pointers are like envelopes in my little analogy. The dereference operator opens the envelope to either put something into the envelope or take something out of the envelope. The address of operator is the writing of the address on the envelope so that when the computer opens it, it knows where in memory it's opening to. So it's kind of like a portal in that way. And then the pointer is the envelope itself as you carry it around through memory. So let's go through the example provided. We have a very simple integer, and we'll call it a, and we'll set its value to 0. And we'll create another integer as a pointer. So it's a pointer to an integer, p of a. I just put the leading p underscore as a prefix just for this example. And I'm going to assign it to the address of a. So construct a little envelope. On the envelope, write the address of a. And now we have a little envelope to carry around. So now we can take p of a. We can dereference it. We can open the envelope. And we can write in a 5. Okay. C is typed, so it's an integer. And it's a pointer to an integer. So if you did p of a equals 5.0, that would fail because this is a floating point value. Okay, this is an integer. So it's very simple. You can construct an integer. You construct a pointer to an integer. One little caveat in reading these notations is pointer notation and const notation read right to left, not left to right. So when you declare variables in C, you read them this way. You don't read them that way. So if you wanted to say int pointer, no, you say a pointer to an int. If you wanted to say a pointer to a double. Right. If you wanted to say you would say D2 is a pointer to a constant double. You would not say a double that's const is a pointer. That doesn't make any sense. D2 is a pointer to a constant double. So the type declarations in C are read right to left. And I think that's not obvious when you're learning C. Okay. So why do you want to do this? Int main. And to be pedantic, in the example given, this is wrong. So he declared int. Oh, he's using floating point values. Okay. He declared float w. Okay. W equals 5.0. And then he called input address of w, like that. Okay. So we have a float, regular floating point value. We put 5 in that value. We construct an envelope by taking w, taking the address of. This object here, right here, constructs the envelope and sends an envelope to input. So input doesn't get the floating point value. It gets an envelope with a reference to the floating point value in it. Okay. So you have to declare input will accept an envelope. It has to accept a pointer to a float. So you read it right to left. And we're going to call that pointer to a float SW. Okay. So we're going to take SW. We're going to dereference it. That opens the envelope. Where's the example? Oh, he calls scanf. Okay. And we're going to write the value 10.0 into it. In the example given, he called scanf, which reads a value from standard input. And it's subtle because scanf expects a pointer, so you don't have to do any, you don't have to construct an envelope because you already have your envelope right here, SW. It's already a pointer to a float. So scanf is declared something similar to int scanf blah float SW. So it's going to already accept an envelope, so we don't have to construct another envelope. Scanf is a little bit more complex than that, but you can just think of it as already expecting a pointer. It's already expecting to receive an envelope, so you don't have to do an address of to make a new envelope. That would be the equivalent of taking your envelope and putting it inside another envelope and closing that second envelope. So you'd be constructing float pointer P of SW. So you would have a pointer to a float, right to left. So when scanf reads the value, it reads it into SW. Here we're opening the envelope and we're putting in the 10, and then we're returning back. So if we print here, percent, it's not D, it's LF, LD, something. This is wrong. Whatever the printf notation for the floating point value is. LD, maybe? And then it accepts a value. This will print 10. Why will it print 10? Because we didn't send W over there, we sent W as a reference inside our envelope. So we opened the envelope, we wrote in 10, we close the envelope. When we exit this function, W now has the value 10 in it. Okay? So this seems like we're just moving stuff around. Why do we care? Let's say we had a function that declares an array. Okay? A pointer to an integer. And we're going to say that pointer to an integer is equal to malloc size of int times 1, 2, 3, 4, 5, 6, right? Massive. Make this huge array. Allocate all of memory. Who cares? We're going to take a function, and it's going to take an integer pointer, so a pointer to an integer, P. Okay. For int I equals 0, I less than big ass number, plus plus I. Don't get hung up on the plus plus I. You can put it before or after in this case, and it doesn't matter. Open P, set it equal to the value of I, and we're done. So we construct this huge array as an allocation out of the heap. We call function, construct our envelope, It's going to call our function. It's going to receive the envelope, pointer to an integer, and it's going to go through the entire array 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to big ass number, right? So if we didn't have pointers, if we didn't do that, then we would have to declare a function. We don't have a way of doing this abstract envelope notation, so we would have to declare a function that receives an array of that size. And if you wanted to have a function that takes an array of a different size, you'd have to have a separate function, even though they do the same thing. So the pointers let you stand back and operate just with this abstract idea of a pointer into, an envelope into some larger piece of memory, and you don't have to declare all of your sizes up front. So that's one motivation. Another motivation is if you had to pass the entire array into this function, you would declare, 10 gigabytes, whatever this size of this thing is. You call this function. If you didn't have pointers, so if this wasn't there and this wasn't there, and you were sending in an array, you would have to copy the array. So now your memory goes, 10 gigabytes to 20 gigabytes to call into this function. You change all the values, and then you return the function, return the array, and so your memory goes 10 gigabytes, 20 gigabytes, 10 gigabytes, and one of the slowest things in the computer is allocating memory next to I/O costs. So, arrays let you, deal with things as these lightweight little envelopes, and you don't have to carry around these big, heavy arrays everywhere. You can just send these pointers around. Your signatures get real nice because they're just pointers, they're just envelopes, and everything's very lightweight and cheap because pointers are the size of a single word on the processor. So on a 64-bit machine, they're only 64 bits long. And a processor can deal with 64-bit numbers very, very quickly. So I hope that helped. Oh, there's one more question. Why the periods? The question is why the periods? So the periods are because he could have made it more readable. So he had a float. What did he say? W. And he said W equals 5 dot if, right? That's what the example says? No, less than or equal to. If W is less than or equal to 5 dot, why 5 dot? What does the compiler actually see? If W is less than or equal to 5.0. The dot just casts it to a floating point value. That's all it does. It just tells the compiler, I don't want the integer 5, I want the floating point value 5. And it's so the compiler can deal with types. I think, and some languages do this, they require the trailing 0, but C doesn't do that, and so some people leave it off. I feel it's less readable. I myself always put the trailing 0 after there. So I hope that helped. Good night.